Last week, we introduced quantum mechanics with the many-path formulation, and this week we applied it to the hydrogen atom using the semi-classical approximation. And with that, we found that electrons rotating around the proton in the hydrogen atom can only do so at some uh, orbits with well-defined radii. And when the electron transits from one orbit to another, it will emit or absorb a photon. And that corresponds to the absorption and emission spectrum of hydrogen measured experimentally. So that's a clear signature of quantum physics. We obtained wave equation for the amplitude of probability to find a particle at some position x. That's the Schrodinger equation. We didn't solve the Schrodinger equation or used it because that's beyond the scope for this course. However, here is an example of a solution of the Schrodinger equation for a free particle. So what is plotted is the real part of the wave function as function of x. And you see that it's oscillating with x, and it's not localized at a given point in x. So because it's an amplitude of probability to find the particle at a given position, you see that this means we can find the particle at different position in x. In fact, what this means is that the particle is at all these positions, and it's only if we do a measurement that we have a probability to find it at a position or another. But intrinsically, it means that the particle is not at a given position, but it is at several places at the same time. And so because this is a time-dependent Schrodinger equation, if you solve it, you have a time evolution of the wave function, and that's an example for a free particle. More interestingly is quantum physics also has a striking implication like the quantum tunneling effect. So as this drawing shows, if you are in a quantum mechanics, you can go through a wall with some non-zero probability. And indeed, if you solve the Schrodinger equation with a wall represented in green, so that the potential energy, which is zero everywhere except at some region in space where it is at 20 arbitrary units, and you send a wave function, a wave packet, with an energy which is below the height of this barrier. So it has only a bit less than 15 arbitrary unit energy. And in classical mechanics, you will not have enough energy to go on the other side of the wall, of the potential barrier. But in quantum mechanics, the situation is different. What happened is part of the wave function is reflected and part is transmitted. So that's something which you will not have if you were purely in classical physics. And interestingly, when you look at time after the wave packet hit the wall, you have part of the wave function which is transmitted, part which is reflected. But remember, this is the amplitude of probability to find the particle at some position x. So what we see here is that the particle is not either on the left or on the right. It is actually both on the left and on the right. It has been reflected and it has been transmitted. When you do the measurement, you only find it on the left or on the right. But before you do the measurement, it's both on the left and on the right, which is a striking implication of quantum mechanics. So we then move to light. The problem is we can't start with a Schrodinger equation to describe light. The reason is that the Schrodinger equation is for massive objects. You see there is a mass and in the denominator for the kinetic energy term. It's also non-relativistic because it starts from a kinetic energy which is half mv squared, or p squared on 2m, and we will see when we will do relativity that this is not the right expression in relativistic kinetic energy. But if you look at light, at the photon, it is massless. It is relativistic because by definition it's moving at speed of light, and its energy is expressed differently. It's h nu, where h is a Planck constant and nu is a frequency. So clearly the Schrodinger equation is not the right starting point to describe light. In fact, light is described by electromagnetic waves of frequency nu, which obey Maxwell equation. And Maxwell equations are classical. They are wave equations like the Schrodinger equation, but for massless object propagating at speed of light. And in particular, there is no h bar in it. So it's not a quantum equation. So we started with an action for a photon, which we wrote using the known energy of a photon h nu. And what we found is something which is proportional to the time, because the energy is constant, so the action is proportional to the time traveled by the photon. And if I write an amplitude of probability for the photon to go from one event to another, I have to sum over all the paths as usual. But the phase is the action divided by h bar. And as you see, the action is proportional to h bar. So when you divide by h bar, there is no h bar anymore. And that's what makes light a bit interesting and specific, despite the fact that you are writing things in quantum mechanics. You have no h bar in your final equation. So we then took the equivalent of the classical limit, which, because there is no h bar, we can't use the action much greater than h bar. However, when we have the frequency nu times the propagation time much greater than 1, that's the same thing, that's equivalent. And what we found is stationary time or least time principle, which is the Fermat principle. From that, we could derive the Snell-Descartes equation for reflection and refraction. We then introduce a Mickelson-Morley experiment. So it uses an interferometer. So the idea is you send a beam of particle through a mirror at 45 degrees, and that splits the beam of particle in two. So part of the particles are reflected to the up mirror, and part are transmitted and then reflected from the mirror on the right. Then there are particles, or part of the particles are then collected together on the screen in the bottom. So that's a detector. So if you tune your detector or your interferometer such that both paths have the same action, you will have a constructive interference on the screen. However, if you look at a different point on the screen, you will different point x, you will introduce a small change of phases between the both paths, and then what you observe on the screen is a series of interference fringes. So what happens when your detector is using photons? And the idea was, if it's moving through the ether, then the path on the right gets longer than the path going up. And because of that, you expect a small delay in the collection of the particle, which introduces a small change of phases. So instead of having the main fringe centered in the screen, you will have a small shift. The idea was then to repeat this experiment at several times during the year, because the Earth rotates around the Sun, implies that it's moving at a different speed through the ether, if we assume that the ether is around us and it's not moving with the Earth. So you would expect to see a different shift as function of the season where you do the experiment. And it turns out that they never found any shift. So whether you do the experiment in winter, in summer, in spring, autumn, you always find the same position of the main fringe. And that was interpreted as a non-existence of the ether.